So we've proved it. You know, we've proved that is equal to that. Now that's only half the story, right? Because we've sort of done this part. Now we have to go the other way. Okay? So we've only done that's equal the identity function. Now we have to go the other way. So now we have to show the. So if we take these two and reverse them, right? Because that's what you've done here. So this is using functions, and this is using elementary group theory with just elements. All right. Okay. So take these two, swap them around. So we'll have. This is what we're trying to prove now. G of f, f inverse g. Now what set, what letter, capital letter will I put here? What's going on here? Remember the rightmost is what you do first. So G inverse, that's what you do first. So what's going on? So G inverse, so that's there's your G inverse, and there's your F inverse. Okay, so we're doing this one first. Now G inverse starts with element little c, okay, and takes you to B, takes you to A, and then F brings you back to B, and G brings you back to set big C. Okay, so if you do whoop, you end up not having done anything in set C. So your this will be C. Hope you followed that. Right? So G inverse F, G takes you back to set C. So that product, you know, do this, then this, then this, then this. Remember, from right to left. That's the same thing as just doing nothing inside set C. So you put a C here and an A there because you started in set A. You went F, G inverse A, and you ended up where you started with in set A. So A here, and similar logic. So a C here. It's a bit subtle, but don't forget it. All right. All right. So now we have to prove this. So it's sort of similar to this. So we'll do this fairly quickly. All right. Think of that as a unit. So you've got 1, 2, 3. This is think of that as a composite function. So we've got 1, 2, 3 functions. So it's associative. We can rewrite this as G and then F of F inverse G inverse okay. Now these three also associative, so we can change the brackets, so we can rewrite that in the following form. Okay. Okay, now what's this? What is this? So you're doing F inverse first. F inverse first. So you're starting in set big B. You do F inverse first, and then cancel it by F coming back. So effectively you just stayed in set B, big B, right? So you do F inverse first, so you're starting in B and you go to A, set A. And then followed by F takes you back to B. So this here is IB. Yeah, so that's IB times G inverse. Is that right? Okay. Now let's rewrite that. Now from theorem 29. Okay, so now G inverse. That's just, so this operator just gives you just G inverse, right? So it's the do nothing. So you will get G G inverse, and that is equal to IC. I can see that because you start with this, you get back, you're starting with G inverse, you're here, you apply G again, so you're back to C. So you didn't do anything, you just stayed in C, effectively. So the identity function for set C, which is IC. Alright? Well, there it is. So we have an inverse, right? It works both ways. So it works that way, and then when you swap it around, you get this. So we've proved theorem 33. Now, if you have an inverse, if you have a function and you have an inverse, this from theorem 30, this f is bijective. Okay, and you can swap the roles of f and g. So if g is the inverse of f, then f is bijective. That's theorem 30. But you can also say that f is the inverse of g, therefore g is bijective. Okay. Now, simply, this is the inverse of that, therefore this is bijective. But this is also the inverse of that, so this is bijective. Alright? So these two composite functions are both bijective. Alright? Now we're going to have theorem 34, and here's the punchline, here's the pot of gold at the end of the rainbow that I've been promising several times throughout this lecture, long lecture. Have you guessed what I've been hinting at several times? So we've got, we talked about associativity, the identity operator which acts like the unit. We've got associativity. Now we need closure. How do you get closure? Well, let's take this is set A and mapping to set A, and let's assume that f is bijective. Okay? And G is bijective, then if where's G? G. I'm not so sure that whether G goes back to A or not. They just F maps A to A, and G also maps A to A. Okay, I think forget about that. Okay, so you have two functions. They're both bijective. So F and G are bijective. Okay, and they both map A to A. F is bijective. G is bijective, and therefore FG is bijective. Where did we prove that?